Hello and welcome to today's class. I'm Mr. Kimwei, and today I'll be taking you through topic 8 in quantitative techniques, which is Introduction to Calculus. So to start with, calculus is a mathematical analysis that analyzes the change of one variable when another variable changes. Normally we have two types of variables, which are usually the independent variable and we have the dependent variable. When we analyze the rate of change or the way one variable, which is usually the independent variable, changes in relation to the independent variable, then that is what we refer to as calculus. Calculus is divided into two broad categories, where we have the differential part, we call it differentiation, which deals with the rate of change and finding the slope of a curve. And two, we have the integral part, which is integration, that deals with finding the area under a curve. The importance of studying calculus, and this simply refers to the areas where calculus is applicable in business operations, is one. We use the knowledge of calculus to measure maximization of revenue, sales, profits, etc. When we want to know when can we be able to maximize, then we use calculus. Then two, we also use the knowledge of calculus to measure the minimization level of costs, losses, and wastage. Normally in businesses, we usually aim at minimizing costs, aim at minimizing wastage, and therefore we'll apply the knowledge of calculus. And then three, we also use calculus to do marginal analysis. For example, if we are given total revenue function and we want to find the marginal revenue function, then we can use the knowledge of calculus, and vice versa. We can also find the total revenue function from the marginal revenue function. Under marginal analysis, we can also be able to find the total cost function when we are given the marginal cost function, and vice versa. Then number four, we also use calculus to solve several business problems that require us finding the area under a curve, and that can be, for example, if we are asked to find the profit, for example, for a certain number of days and so on, we can also apply the knowledge of calculus. So we'll begin on these two categories, as I said, of calculus. And the first category is differentiation. So differentiation is concerned with finding the rate of change of a dependent variable. And the keywords here are dependent and independent variable. The dependent variable usually is a variable that changes in respect of the independent variable, and therefore when we look at how the two changes, then we call it differentiation. And how we do differentiation is we follow just a simple rule of drop and take, and we are going to have an example of what we mean by drop and take. And when we are given, normally here we use a linear function to demonstrate how to differentiate. And therefore, when we are given a linear function as y is equals to x raised to power n, then when we calculate or when we solve and differentiate, we call it dy over dx. So when we find dy over dx of y is equals to x raised to n, then first of all, we will bring the n as the before that particular x, and then we subtract the power by 1. We reduce the power by 1, and that is what we mean by dropping and taking. So first we'll drop this particular n before the x, and then we'll also reduce the power by 1. For example, if we have a numerical example and our function here is y is equals to x raised to 2, that is x squared, then first of all we drop this 2 so that it becomes 2x, then we'll go and reduce the power by 1 so that eventually it is 2x, and this is the same as 2x raised to 1, which is the same as 2x. I've just avoided writing here 1, and therefore it just remains 2x raised to 1. When we have a constant in that particular linear function, for example, example 2, when we have a constant, this is y is equals to, the function is y is equals to 6x raised to 4 plus 27. The 27 is a constant. It's the same as writing 27x raised to 0, because a number raised to 0 is 1. So it's the same as 27 times 1, which is just 27. So if we are asked to differentiate this function, which is 6x raised to 4 plus 27, then to find our dy, because we are differentiating in respect to the x, then we will drop this particular 4 so that it becomes 6 times 4. Then we will reduce that power 4 by 1. We reduce the power by 1, and therefore it becomes 6 times 4 is 24. Then x is raised to 3, because we have reduced this power 4 minus 1. But then here, when we demonstrate how then do we differentiate a constant, it disappears. How then does it disappear? Because this is the same as we had explained here, is the same as 27x raised to 0. First of all, we say when we differentiate, we will drop the power. So that means this power 0 is dropped here so that it becomes 0 times 27x, then we reduce the power by 1. When we reduce the power by 1, it becomes 27x raised to power minus 1. But then because we are multiplying by a 0, then a number multiplied by a 0 becomes a 0. And therefore, the constant disappears. And the final answer will be 27x raised to 3. So when you differentiate a constant, then the constant disappears. And when you move to example 3, differentiate our function, which is x squared plus 6x raised to 4. We are differentiating it in respect to y, then it is dy over dx, which is, now we'll drop 2 so that we have 2x here, then we reduce our power by 1 as I've demonstrated here. Then the second part, we have 6x raised to 4, therefore we will drop this 4 so that we multiply it as 4 by 6, then we reduce the power by 1 so that it becomes 2x then plus 24x raised to 3. So having learned on how to differentiate a function, then we can look at the types of derivatives, and basically a derivative refers to differentiating a function. And we have 2 types of derivatives. We have the first derivative and we have the second derivative, but we can move even as much as the third derivative or the fourth derivatives. When we find the derivatives, we differentiate equations just the same way we had done earlier on, and we'll use this example to know what first derivative is and second derivative is, and then we'll also move at the uses of these derivatives. So when we say the first derivative, we refer to differentiating an equation only once. And if we are given an equation as y is equals to x squared plus 6x raised to 4, then the first derivative is dy over dx. That is, we are differentiating y with respect to x only for once. And therefore, as we had said earlier, the rule is drop and take. And therefore, we drop the power, and then we also subtract 1 from that particular power. So this is x squared raised to 2. This is x squared raised to 2. And therefore, we'll drop 2 so that it becomes 2x. And then we will subtract 1 from this power, which is power 2, so that it becomes power 1. Then for the second part, we have 6x raised to 4. We'll drop 4 so that it becomes 4 times 6. Then we will reduce the power 4 by 1 so that it becomes power 3. So that our first derivative becomes 2x plus 24x raised to 3. On to our second derivative refers to differentiating an equation for the second time. That is, we are differentiating the first derivative. From our equation, we had 2x, then plus 24x raised to power 3. And therefore, this was the first derivative. When we differentiate for the second time, it becomes d2y over dx squared. That is d squared y over dx squared. This is how we write the second derivative. Then it will be the same rules apply, in that here it is the same as having 2x raised to power 1. We drop the power so that it becomes 1 times 2, and then we subtract the power by 1 so that it becomes power 0. A number raised to 0 is 1, so that eventually we remain with 2. Then for the second part, we'll drop the power, which becomes 3 times 24. Then we will subtract the power by 1 so that it becomes 72x squared. So that is how we find the first and the second derivatives in case we are asked to find these particular derivatives. When now do we use these derivatives, or where do we apply these derivatives? We apply these derivatives to find the minimum or maximum points, and also to identify maximum or minimum points when plotted on a graph. How then do we find? We'll have an example, and we have used an equation on finding we have an example where we are given y is equals to x squared minus 4x plus 3, and we are asked to state whether it is a maximum or a minimum point. We have to prove, and we have said we'll go and apply the knowledge of first and second derivatives. First of all, we find the first derivative from our equation here, which is x squared minus 4x plus 3. Our derivative will be, as we said, when we differentiate, then we drop the power, then we subtract that particular power by 1, so that our first derivative becomes 2x minus 4. Our second derivative will be to differentiate the first derivative, which is 2x minus 4. When we differentiate, then we drop the power here, which is 1. So when we drop, it becomes only 2. Then x disappears because it is like raising x to power 0, which is the same as 1. So our second derivative is 2. The first derivative. So how then do we find? How then will we be able to state whether this is a maximum or minimum, as we have been asked in our particular question? Then we will use the first derivative, which is up here, to find the critical point. How do we do that? We equate the first equation to 0, the first derivative to 0. The first derivative was 2x minus 4, then we are equating it to 0. When we solve by taking 4 minus 4 to the other side, we'll get x as 2. So the value of x at that critical point is 2, and therefore this x is equals to 2 is the critical point. That is the use of the first derivative. Now, the second derivative will demonstrate to us whether it's a minimum or a maximum. And the answer here is, if the second derivative is positive, that is, if it is a plus, then it is a minimum point. If the second derivative is a negative, then that particular point is a maximum. And then how do we know? I said we'll use the second derivative. We had calculated it earlier. Then we got the second derivative as 2, which is positive. As per our rules here, which I've indicated here, if it is positive, then it is a minimum. And I've also indicated here, and I said, if the second derivative is greater than 0, that simply means it's positive, then it means it's concave up, and therefore that point is a minimum. So if you are given an equation and you calculate the first derivative, we get the critical point, and the second derivative, we get it as a negative, then it will have been a maximum point. If we want to get the coordinates for that particular minimum point, then we use that particular 2, we got here as the critical point, and we'll come and substitute it. We'll come and substitute it in the equation we had been given earlier on. Y is equals to x2 minus 4x plus 3. And here when we substitute, in the place of x we have 2, eventually we arrive at minus 1. And therefore the minimum point, the coordinates for the minimum points are 2 and minus. And this 2 is what we have gotten earlier on, and minus 1 is the other coordinate for y. So as we had mentioned earlier on, calculus is divided into 2 categories. We had differentiation, which we have just done earlier, and then the second part is integration. So integration is just the opposite of differentiation, and I've stated here is the reverse of differentiation, and this one is aimed at finding the area under a curve. And therefore, when we are doing differentiation, we just do exactly the opposite of what we did in differentiation. The simple rule here is add and divide. And what we are simply adding here is the power, then we are dividing that particular power that has been added. That means the result that has been added as the new power. For example, given that y, which is a function, is kx raised to n, and n is the power, k is the coefficient of x, then what we do, we will add, as I've indicated, we'll add this power by 1, and then that particular answer, which now becomes n plus 1, is what we divide as I've shown. We also have to show the integral part to show that we are differentiating this particular function, and then we'll also have a constant, which is represented by our letter C. A numerical example, we'll have 2, and the first one is y is equals to 6x raised to power 3 plus 2x plus 3. Given this function and we are asked to integrate, then first of all, as I've said, we have to show with that integral sign so that we are able to know if we are integrating or not. And when we solve, we follow our rule as I've indicated up here. As I've indicated up here in our rule, and I said first we start by adding the power. So in our first part we have 6x raised to 3. When we integrate, we add 1 to this power so that it goes to 4. Then we divide, as I've shown here, by that new power, which is 4 for this case. For the second part, we had 2x. And this is the same as x raised to 1. As we said, there's no point of showing a power 1 because it does the same. So when we add the 1 to this power 1, it becomes x raised to 2. And then we divide by that new power, which is 2. Then here we had just 3 as a constant. Because we are differentiating with respect to x, as I've shown here, then it becomes 3x. This is the same as x raised to 1. And therefore, because we said when x is alone here, it is the same as having 3x raised to 0 to power 0. Because a number raised to 0, this one becomes 1, that's why it is just 3. So if we add a power 1 here, then it becomes 3x raised to power 1, which is just the same as 3x. And therefore, finally, we add a constant as I've shown. And therefore, we'll come and divide 6 divided by 4, 2 divided by 2. That is 2x squared divided by 2. And then here, so that our final answer becomes 1.5 x raised to 4 plus x squared, then plus 3x plus c. You must show that particular constant. When we move to example 2, we are also going to do again a second example so that we are able to learn better. And here we are given the function as y is equals to 8x raised to power 3 plus 4x raised to power 3 plus 5. And therefore here we have the integral sign. As I said, we start with that so that we show that we are integrating. Then we are integrating this particular function with respect to x. That's why I'm adding the x. With respect to x, then we add a constant. What happens here is the same rule applies as we have shown. in that we are adding the power, then we divide by that particular power. For example, the first part we have x, 8x raised to power 3. The power here is 3, we add 1 to that particular power so that it becomes 4, then we divide by that 4, which is the new power. For the second part we have 4x raised to 3, and this simply means we are adding this power 1 so that it becomes 4, then we divide by that 4 eventually. Here we have 5, which was just a constant, but because we are differentiating it with respect to x, as I have demonstrated here, when we have 5 alone, it's the same as it being 5, it's the same as it being 5x raised to power 0. And therefore, when we differentiate, it becomes 5x, then we have a constant c. And therefore, the answer here is found by simply dividing 8x squared divided by 4, we get to 4x squared divided by 4, then we have 5x, then eventually we have a constant. This is all about integration, and an important point just to note is that it's just the opposite of differentiation. Now, the key areas, as I mentioned earlier, where we apply the knowledge of calculus is in optimization. That is when we want to maximize sales, we want to minimize costs, and so on. And therefore, basically we have formulas that normally we usually use when we are asked about, these are the things we are asked during exams, and therefore it is good that we learn the formulas first before we proceed and do an numerical example. The first thing that you are supposed to know is that in business, profit is calculated by finding the difference between the total revenue and total costs, which is profit is equals to total revenue and costs. Now, revenue is abbreviated as R, then the cost as T. Sometimes we use TR, just meaning total revenue, and TC, meaning total cost. How do we find revenue? This is the amount we generate from the sales, and basically we multiply the price times the quantity of commodities that we are selling. And costs are also divided into two. We have fixed costs and we have marginal costs, and therefore when we are finding the difference, then we have fixed costs. When we want to find the fixed cost, we take the total cost, then less marginal cost. Normally we call them variable costs in our day-to-day activities. Then we can also be asked to find the maximum point, and how do we find the maximum point? We'll equate the marginal cost to marginal revenue. Marginal cost refers to the total cost of producing one extra unit of output, while marginal revenue refers to the revenue that we get as a result of selling one extra unit of output. And this is also demonstrated here at maximum point, marginal cost equals marginal revenue. Therefore, how then do we apply these two? So, given marginal cost, then if we want to get the total cost, we have to differentiate, to integrate that function, which is marginal cost. It simply means the opposite. When we want to get the marginal costs, then we will differentiate total costs. So it's just the opposite. One way to the other. From total costs to marginal costs, we differentiate, and then from marginal costs to total costs, we integrate. The same way to marginal revenue. Sometimes in an exam, you are given the marginal revenue function and you are asked to find the total revenue function. You need to integrate, and if you are asked to find the marginal revenue function from total revenue function, then we will differentiate. So from here, we are moving to examples where we are going to look at the numerical examples of application of these particular formulas as follows. So having looked at the various formulas on how we can be able to apply the knowledge of calculus, then we'll have two examples that we'll use to show how how to apply that knowledge of calculus in optimization. The first example says a small company produces and sells X units of a product. the total cost function and total revenue function are as given below. So total cost function is 100 plus 6x, and the total revenue function is 12x minus 1 over 50x raised to 2. So for easier calculation, we'll convert 1 over 50, this fraction, into a decimal so that we are able to calculate well. We are asked to determine Roman 1, the profit function. As we had stated earlier, profit is the difference between total revenue and total costs. So if we are asked to determine the profit function, we'll simply have the total revenue function minus total cost function. Our total revenue function was 12x minus 1 over 50x squared, which we had it here. Then we are subtracting 100 plus 6x. The whole of this is the cost function, and that's why I've put it into the bracket so that it is not affected. And therefore, the profit function will be 6x, which is 12x, minus, because we have a minus outside here, then this one becomes minus 6x, then minus 0.2, I've just converted this fraction into decimal, 0.02x squared, then minus 100, because this is minus and inside we have 100, so the profit function becomes 6x minus 0.2x squared minus 100. Roman 2, we are also asked to determine the level of output to maximize profit, and we said, first of all, for us to maximize output, we must be able to differentiate the profit function in respect to Q. Q is the quantity of output, and therefore, after differentiating, then to get the level of output to maximize profit, we'll have to equate that answer to 0. And therefore, we find the first derivative, which is dP in respect to dQ, that is where differentiated profit with respect to quantity. Of course, it is this function, the profit function we are differentiating, and therefore when you differentiate 6x, we get x. As we said, we subtract the power, then we bring the coefficient on this other side so that it becomes 6x minus 0.04x. This is bringing 2 on this other side. When we multiply, then we reduce the power by 1. Now, after differentiating, that is getting the first derivative, we equate that particular first derivative to 0, and therefore we bring this 0.04 on the other side. It becomes 6 is equals to 0.04x, and therefore x will be equal to 150. So this 150 is the quantity of output, or the level of output that will be able to maximize profit. Now, our third part was to find now the maximum profit. So having found the quantity that will maximize profit here as 150, we will come and substitute this 150 into the profit function we had found earlier. And therefore, our profit is supposed to be 6x minus 0.02x squared minus 100, but we know that x is 150 as we have calculated earlier, and therefore when we substitute, we'll get our maximum profit as 350. We'll move to our example 2 lastly, and our example 2 says the following is the demand function and average cost function of a commodity produced by a company. So here they have twisted a bit because we have been given the demand function. The demand function normally is denoted by P, and the average cost is AC. So where P is the price, as we have been told, and Q is the output. And therefore here we are using P and Q. We are asked to determine Roman 1, the total revenue function. You remember when we were talking about the formulas, we said total revenue is a multiplication, or is a multiplication of price and quantity. And therefore, we already have the price, which is represented by P, which was given as the demand function, which we are going to multiply by Q. So we are multiplying the whole demand function by Q, and therefore we get the revenue function as 50Q minus 0.5Q squared. That is when we multiply Q by whatever is in the bracket. 2, we are asked to determine the total cost function. The total cost function will be found by multiplying the average cost function that we had been given by multiplying average cost function by Q, which is the quantity. And therefore, the average cost function had been given as 10 plus 1.5 Q. Then we are multiplying by Q. And this one gives us the total cost function as 10Q plus 1.5Q squared. Roman 3, we are asked to calculate the profit or to show the profit function. And as we stated earlier, profit is the difference between total revenue, which we have here, and we have it as a function, and total cost as I indicated here. And therefore, we have the total revenue function minus the total cost. Remember, this minus affects everything that is inside the bracket because this is the whole total cost function. And therefore, when we subtract, here we have 50Q minus 10Q, we have 40Q. Then here we have minus 0.5 Q squared. Then we are again minus it because this is a minus plus. So it is minus 1.5 Q squared, and we have the answer as 40Q minus 0.2 Q squared. This is the profit function. In part 4, we are asked to calculate the level of output to maximize profit. As I've said, first of all, we will differentiate this profit function above in respect to Q. And when we differentiate 40Q minus 0.2Q squared, we get 40 minus 0.4Q. Therefore, at maximum profit, we said this first derivative is equal to 0. And therefore, it will be 40 minus 0.4Q is equals to 0, where we find our quantity. This is the level of output as 100. So this 100 will come and substitute it in the profit function we found here to get our maximum profit. Our profit function was 40Q minus 0.2Q squared, and therefore where we have Q, we'll substitute by 100, and therefore we get our maximum profit as 2,000. Thank you, and see you in our next class.